you tonight. Sorry if I'm not in person. It was a bit of a short notice indeed, but also I'm a recently new minted father, so with the baby around, I'm still not traveling for the minute until she's
Congratulations! Congratulations! How old is it now?
Yeah, 2.5 months.
2.5 months. So it is by a long, although I'm not quite officially a member, we would, of course, reach out and it would make it by far our youngest member.
Yeah, so anyway, so I'll move on to the talk. So tonight's presentation is entitled Einstein's Relativity Tested to the Limit with Pulsars. So it's a talk of in three parts basically. So first I'm going to tell you a bit about pulsars, which turns out to be the very kind of objects that I study, as part of my research. I say that because sometimes I give talks on, I don't know, black holes or some other topics, which is not directly what I'm working on. But pulsars are. Then I will tell you just about enough, for you to be able to follow the rest of the presentation. But it's not a talk just about pulsars, if that makes sense, because I could give a sort of 12-hour lecture just on that. So I'll give you the minimum. Then I'll talk about relativity, and I imagine that most of you have heard of it and know maybe some of the facts about relativity, but are probably not specialists. So I'll tell you a bit so you understand roughly what it is. And then I will tell you how we can test that theory using pulsars, which is the third and last part. So, okay, so first round about pulsars. So pulsars are magnetized, very fast spinning neutron stars. So neutron stars, so now I need to tell you a bit what they are as well. Neutron stars are these very, very tiny objects. We're talking about 10 kilometers in radius, but they contain about 1.5 times as much matter as the sun. So about a typical neutron star would have a 1.4 solar mass, so times the mass of the sun, basically, in terms of mass. So this means that if you shrink all that matter into a tiny object the size of a city, you end up with a really, really high density. And so we're talking about densities which are as much as shrinking a mountain to the size of a dice, basically. Or another comparison would be to take all of humans on Earth and shrink us all to the size of a sugar cube or a dice. So they're extremely, extremely dense objects. And as a result, they have very large gravitational fields. And also you can imagine that inside these objects, matter, behaves in a rather strange way because this is extreme physics. And I won't talk about, the details of like inside neutron stars and all of that, but you can ask me questions if you have any later. The other thing that's very special about neutron stars in general, but especially pulsars, is that they have very large magnetic fields. So a typical neutron star would have a magnetic field of about 10 to the 12 Gauss. So this is the exponential notation, means basically that it is 1 followed by 12 0, if you were to write the number in full, right? When 1 with 12 0, which is basically 10,000 billions Gauss. Now the Gauss is the unit, a bit like we use meters to measure distances. The Gauss is the unit we use to measure magnetic fields. And to give you a sense of scale, the ambient magnetic field on Earth, like if you take your compass and you find the magnetic north, like the magnetic field that aligns the arrow towards the north is about 0.5 Gauss. Okay, so So we're talking about like something of order, on Earth, like that sort of fields we see typically are of order of a few Gauss. And there we're talking about 10,000 billion Gauss. So extremely magnetized objects. In fact, they're the most magnetized objects in the universe that we know of. And also they spin very quickly. So they take between about 1 millisecond to something like 10 seconds for the slowest to make a full rotation. And in fact, there was a big discovery announced about a week or two ago from led by a colleague of mine at Manchester. They found the slowest ever detected pulsar, which spins in 70 seconds, so 70. And this is the slowest by essentially a factor of 3. But most pulsars are somewhere around a few milliseconds to a couple of seconds. And the reason why some of these neutron stars, we call them pulsars, is because they blink. So they're pulsating stars, hence the word pulsar, which is a contraction of that. And so the way they blink is because along the magnetic field of the objects, so imagine the object spins along an axis, say like this, which is vertical, but the magnetic field of the object, the north and the south magnetic poles don't need to be aligned with the spin. Just like for Earth, like the spin, right? The North Pole is not aligned with the location where the magnetic North Pole is. The magnetic North Pole is located somewhere in northern Canada in the islands. So a couple of 1,000 kilometers from the actual true north of the rotation of the Earth. And so this magnetic field somehow focuses particles that are in the surrounding of the pulsar. And these particles emit light, and the light that's produced is emitted along the magnetic field as a narrow cone. So as the star rotates, you have essentially a beam of light which sweeps across. And if you're lucky and you're at just the right position compared to the geometry of the object, you're going to see the radio beam sweeping across the line of sight, and you see a flash of light. So this is how we see pulsar, through this sort of cosmic lighthouse effect. The other thing to perhaps make clear is that most pulsars actually are very faint objects, and most of the light that we emit and detect is actually produced in the radio waves. So typical pulsars, you don't use an optical telescope, looking at visible light to observe them, but instead you use a radio telescope, such as the Lovell telescope that we have at Jodrell Bank. So at Jodrell Bank with the Lovell, we spend about a third of the observing time every year looking at, a myriad of pulsars and doing science with them. So you recognize the Lovell telescope, I'm sure, here on this picture. So we point at pulsars. We know of, and I should update the number, it keeps changing. So, if I'm even like a couple of weeks, then usually there's a few new pulsars found, but there's order of 3,000 pulsars known so far. And about 10% of them are in binary system, which means that the pulsar is a companion star that orbits around it. The most famous one is probably the Crab Pulsar. So this is an image of the Crab Nebula. You probably are familiar with this, a picture like this. It's one of the, favorite objects of optical astronomers, especially amateur astronomers, because it's something you can see in a small telescope or even with binoculars in a dark sky. So the Crab Nebula in the Taurus constellation. And if you can see deep enough, so we're talking about magnitude like 12, if I recall also, there's like a doublet of star right at the center of the nebula. And one of them is actually not just a regular star. So most all of the stars in this image are either foreground or background stars that are in our galaxy. They're not connected whatsoever to the cloud of gas that's there. But one of these two dots, I keep forgetting if it's the bottom one or the top one, but one of them is actually at the center of this cloud. And this is the leftover of a massive star, which was about 8 to 10 times bigger than the sun at birth, and lived, became a supergiant, and exploded in a supernova. And when it exploded, it shed away most of its mass in that explosion. So that's basically the envelope of the star was pushed away and formed this nebula. But the core of the star, where essentially the nuclear reactions take place during the normal life of the star, that core, which is probably a size similar to that of the sun, or similar size as the Earth, rather, then when the star explodes, the core shrinks until it reaches about 10 kilometers. And when it reaches this density, there's enough pressure that's generated to prevent it from shrinking even further, and then it stabilizes and becomes this neutron star, and then might produce these flashes, which then makes it a pulsar. So that's how pulsars are typically formed. And when we observe them with a telescope, like the Lovell telescope, something you might not know is that the Lovell telescope is basically a 1-pixel camera, right? The Lovell telescope on its own does not make images because there's only one sort of antenna, the primary focus. So it's as if you collect all of the light, within the field of view of the telescope, which is about give or take about a quarter of the size of the full moon. And all of the radio light that comes from a patch of the sky about that size comes, into the detector and is all just coming as one stream of data. So you cannot make an image. If you want to make images, you need to put a special receiver that we call a multi-beam receiver, where there's multiple sensors. And typically a multi-beam receiver can have maybe about of order 10 pixels, in case it's not a lot. And if you want to really make like a nice image in the radio, what you need to do is you need to have an array of radio telescopes that work in unison and form what we call an interferometer, a radio interferometer. And you have some that you can see in pictures, like the VLA, for instance, in the US, where you have like this sort of this Y shape of like antennas. But we also have an array like that in the UK that's called eMerlin, and it's made of basically 8 dishes that are across the country. Most of them, smaller than the Lovell, but then they can be connected together. And then when you combine the information, you're able to form an actual image. But for observing pulsar, we don't really need it. But when we observe pulsar, that's basically what we're interested in. So we get the stream of data and we basically form a time series. And the pulsar shows up in the time series a bit as a heartbeat, if you want, at regular interval. And it's the study of the interval in that pulsation, the time between in the pulsation, timing it very accurately, and studying the shape of the pulses and some other properties, which gives us all the science, and all the information that we need to know about pulsars. So pulsar astronomy typically is looking at time series rather than looking at images. So each pulsar, in fact, has its own pulsation that is different from others. So on the little animation you saw before, you saw these spikes. If you were to combine, right, you see individual spikes, but for most pulsars, the one I showed there is actually the brightest pulsar in the sky. So it sticks out, from the noise. But most pulsars, they're in fact so faint that they are buried in the noise. But it's when you look at the fact that they repeat, which means that you can do a process that we call folding the data. So you can basically take the data, the time stream, and you can cut it at the repeat period of the pulsation, and then you can stack these data, and then it makes the amplitude of the pulsation we detect larger. So when you look at this average pulse that's formed, it tends to be very stable for most pulsar, but they each have their own shape. Most of them will look like, a single pulse like this, which is kind of like a bell curve, which is fairly narrow. But then some of them will show like, a very narrow profile with like little kind of like dips on each side. Some might show a double arrow, double peak. Sometimes the peak can be further apart. In some cases, you'll see a train of different pulses. So they're all different, and it depends on the geometry of that light beam that is coming towards us. And each one of them will therefore sound different, right? So if you were to take that stream of data and you were to convert it into a sound, then it can sound like something like this, which would be a fairly slow one. Then this one would be one that's faster, so it's the second one, 0437. This one's 5.5 millisecond, and that's the shape of the pulse of that pulsar. Then there's a Crab Pulsar, the famous Crab Pulsar. Sounds like this. The Crab Pulsar makes 33 rotations per second, so that's why you hear the like super quick. Then Vela Pulsar is another very famous one, so about 11 rotations a second. And then one of the fastest, the second fastest known, is 682 rotations per second. And it sounds like that. So you can understand we usually don't listen to the sound of pulsars. We just do that for show when we give talks, but because that's rather annoying to listen to. So instead we look at the shape of the pulse. Okay, so I've described a bit earlier how pulsars are found, with the Crab Pulsar, which is that you have a massive star, and at the end of its life, it becomes a red giant, or super red giant rather, and then it explodes, as you've seen just here. And after the explosion, if the star is very massive and what's left behind is massive enough, when it contracts, it will reach a point where it keeps shrinking and it keeps shrinking and eventually turns into a black hole. But there are objects that are not big enough, after they've exploded to become black holes. And they become these neutron stars. Which are kind of like intermediate, between, becoming a black hole and becoming, say, a white dwarf, like the sun will become. So in some cases, these stars can be in binary systems. And it's quite common. More than half of the stars in our galaxy have a companion star that orbit them. And so if that's the case, then there might be a time where, you have the smaller star is still there shining, and then you have, like, say, a pulsar that's formed. And then the system evolves and evolves. But then eventually, sometime later, that little star might become a red giant star. And then if you have a configuration for the system where that companion star is close enough from the very compact and strong gravity pulsar, you might reach a point where at the surface of that companion star, matter, like the gravity of the star itself, is basically just about equal to the gravity of the pulsar, which means that the matter on the surface will be very loosely bound. And the matter just needs a little kick, like a little wind or something to then start, leaving the surface. And when it does so, then it gets attracted by the nearest other object, which is the pulsar. And so you might end up having a stream of matter that will get attracted towards the pulsar and will eventually fall on the surface. And when it does so, the matter will, not land in a straight line, but will kind of like still have some of the orbital velocity. So it approaches the pulsar, in a spiral motion, and the spiral becomes smaller and smaller, and eventually it falls on the surface. And so when it falls to the surface in that way, it also brings what we call angular momentum. to the pulsar. So which means, in other words, that it will make the pulsar spin faster, right? And the analogy would be if you have a merry-go-round, right, and you spin, eventually you slow down because of friction, and then you go to a standstill. But if you have like a couple of friends who run and then they just jump, on the merry-go-round, and they jump, kind of, I mean, they don't jump like face on, right? But they usually jump like sort of sideways in the direction, right, that it's spinning. Then you can see it, they give a bit of a little tug, right, to the little kick, little nudge every time they jump on, which can kind of like accelerates or at least helps maintaining the speed. So it's basically the same process that happens when the mass falls onto the surface. And the bottom line is that, as you can see in the movie, the pulsar, which might have slowed down over time and was rotating very slowly, through that process of mass transfer, might start spinning a lot faster, and up to the point where it can spin several hundred times per second. And so this phenomenon gives rise to essentially the fastest spinning pulsars that we know, and we call it pulsar recycling, basically. So all of these binary systems, usually we observe them with a very fast spinning pulsar. And often, like the phase where the mass transfer takes place tends to be rather short-lived. And during that period, the pulsar gets buried by the matter. And so what you see is just a very bright accretion disk. And we call these objects X-ray binaries because they produce a lot of X-ray light that you can detect with X-ray satellites. But when this phase is over, then the pulsar emerges because there's no more gas around. And then you have a very fast spinning pulsar with the leftover of the other star, which, if the star was big enough to turn into a neutron star as well, would be a neutron star. But most of the time, you find a lower mass star, which will end up its life as a white dwarf, like it's going to be the fate of our sun at the end of its life. So a compact object that's cooling down, but is not quite dense enough to be a neutron star nor a black hole. Okay, so I've talked long enough now about pulsars, at least for you to be able to follow what will come in the third round. But for now, I'm going to switch completely gears and talk about gravity and Einstein's theory. So you'll recognize Einstein here, the mustachio guy who likes grimacing. Very, very popular. He was probably the first sort of like superstar scientist, if that makes sense. I mean, scientists don't tend to be superstar, maybe like Brian Cox is maybe, and a few other ones. But, at the, early 20th century, I mean, Einstein really was like, a superstar. Like when he would go somewhere, give a talk, like there would be crowds following him. And it was just crazy. And he's mostly famous for like the work he's done in gravity, although he's done a lot of really amazing other work. So his work on gravity actually started with a theory which he published in 1905, and we call that theory special relativity because it's a theory that's got that applies only to special situations, and these special situations is basically the cases where is theory. The special relativity theory is a theory that is about the dynamics of bodies, right? So it describes things like cannonball motion and things like that. So it's basically a better theory than Newton's theory of dynamics and gravitation, because people found over time that there were issues with Newton's theory, that it was not perfectly predicting observations. So it still works like roughly, but when you can make very accurate measurements, you realize that it's not perfect. So Einstein's theory came basically to correct these sort of like small things that were unaccounted for. And the special one deals only with objects that are moving at constant velocity or are not moving at all. But if things accelerate, or if things are in a gravitational field, then it doesn't deal about it. And I'll come to that. It's the second theory he came up with. And all of this theory is basically can be built, if you're really smart like Einstein, you can basically take two postulates. You can say that the speed of light is constant and equal to 300,000 kilometers per second. And you can also say that the laws of physics are the same for everyone that is moving at constant speed, regardless of where they are in the universe and regardless of what their speed is. And if you just take that as like the two main principles, you can build like the entire theory. So what is that theory doing? Well, there are a few consequences. Some of the most popular are what we call the mass energy equivalence. So you've seen this on, if you went to the beach and people like think they're really cool, they might have like E equals mc squared like on their t-shirt, and they don't really understand what it is, but it's kind of, Einstein, and that's cool. But what it says, right, is that the energy can be equal to the mass of a body. So you can turn mass into energy or energy into mass, and the two are interchangeable, which is not something people had really had realized before. And how much energy can you get from matter is basically dependent on the mass of the object. So if you take the mass of an object in kilogram, and you multiply by the speed of light in meters per second, so 300 million meters per second, and you square that number, you get the total amount of energy that is theoretically contained in that matter, in the energy in joules. And, so that's a lot. For 1 kilogram of matter, you have like, an amount of energy that is in like trillions of joules. And when we do nuclear reactions in nuclear power plant, where we do nuclear fission and we break heavy atoms into lighter ones, we release some of that mass, because when you take like elements that are very heavy, the amount of mass that they contain is actually larger than the total mass contained in two smaller objects. So the difference in mass, when you break the object, comes out as energy in terms of gamma rays and neutrinos and other things. And that can be essentially collected, in reactors and through like the boiler, basically, of the reactor to heat up, water and then activate a turbine. Or if you take stars, they do nuclear fusion. And then fusion in stars, what happens is you have very light elements. And when you combine them together to make a heavier element, the heavier element is actually lighter than the two smaller elements individually. And the excess goes off as energy. And that's how stars shine. So the fact that the mass is less when they're combined, it's because there's binding energy that holds them together, and that binding energy allows some of the mass to be converted into energy. So that's so now you know what E equals mc squared means. There's something else that's actually really strange that happens in relativity, and we'll use this little arrow and bow and target analogy to look into it. So imagine that you have someone who likes archery, has a bow, and then essentially launches arrow towards a target. And let's say that this particular arrow bow setup gets the arrows to fly off at a speed of 200 kilometers an hour. Now, don't ask me. Well, I guess I could potentially estimate, but I don't do archery, so I don't know if that number is realistic or not, but let's just imagine that this is the case. Now, imagine that this person has a friend who goes on a train and very, recklessly and illegally open the window, and that person has the same bow and arrow like brand, right? And, exerts like the same tension and everything, which means the arrow flies off also at 200 kilometers an hour. And imagine that the train is traveling at 100 kilometers an hour. So now if you were to look at the speed, right, if there was like a radar gun or something that could measure the speed of the arrow, as it goes towards the target, I guess you'd agree with me that the speed for the person on the ground would be 200 kilometers an hour. And for the person on the train, it would be compounded, right? So it would be the speed of the train moving forward, which is 100, plus the speed of the arrow, right? Because the arrow is launched on the moving train, so it will add the speed. So then you would have a total speed of 300 kilometers an hour. Okay, so, and that, if you neglect frictions and things, like, is basically uncontested. If you're unsure whether that's the case or not, like that would be the case. Now, imagine that instead we redo the experiment where we shoot light. And here, like, there's some strange contraption. I'm not sure what that is, but it's a light gun. Okay, probably from Star Wars, judging by the contraption. But you can imagine taking, I don't know, like a flashlight, right? That shoots light, or a laser pointer if you want, and that shoots light as well, right? That would be equally good, but probably doesn't look as good on the on the picture. So imagine you have a laser pointer, right? And you shoot light towards a target. Well, so light travels at 300,000 kilometers per second. So then, okay. But then imagine the train, right, is traveling at some speed. And for the example here, let's imagine the train itself travels at the speed of light. Okay. So now if you were to look at the speed, for the person on the ground, you would say, well, the speed is, we call it c, the speed of light, so c, so 300,000 kilometers an hour. Now, what do you think would be the speed for the person, like, shooting light from the train that goes at the speed of light? So if you apply the same principle as the previous example, right, you would say, well, that should be 2 times the speed of light, right? So the speed of light from the light of the light gun itself plus the speed of light from the motion of the train. So you would think of 600,000 kilometers an hour. But then, if you recall, right, from the 2 slides ago, I said that, according to Einstein's theory, the speed of light is basically universal. It's 300 kilometers per second. And then the laws of physics, right, are the same regardless of you being moving or not, as long as you're going at constant speed. So if the train is going at constant speed and the target says that is not moving, then you would imagine that the speed of light measured for both of them should still be the same speed of light. It should not be different. So the answer to that, right, is that if you shoot light from a train moving at the speed of light, it will, be measured to be going at 300 kilometers an hour. So it will not add up to be 600, but it would still be 300. Okay. Now, okay, getting a train to go at the speed of light is rather difficult. I wish it existed. It would make traveling very quick. But even if the train was traveling, like, slower, say 100 kilometers an hour, the speed will still be speed of light. You cannot exceed that. Okay, and now why is that the case, right? It doesn't have anything to do with the fact that light is light, and here you have an arrow, and there's nothing connected to friction or anything like that. The reason is because our reasoning in the first example was flawed. It is not true that you add the speeds to get the compounded speed. Einstein came up with a more accurate formula, which is some equation that involves the sum of the speeds, but then involves some factor that you divide by, which also involves the speeds. But this more complex equation where the speeds are added is such that the faster you go, when speeds are added, the more, the less they add up, in the regular way you think. And so they will add up, but they will always add up to become closer and closer to the speed of light, but will never exceed it. Okay, so that's what we call an asymptotic, equation. So the speeds add, and they'll get like, infinitely close to speed of light or at speed of light if one of the objects is at the speed of light, but it doesn't go faster. But when objects are moving very slowly, like arrows and things that, we see in our day life, the regular addition, is a good approximation. You would need extremely sensitive measurement apparatus to measure, the discrepancy. So that's why Newton's theory, right, and Newton's laws of motion have worked, for like sort of, and we still apply them today. When people look at cannonballs and things, you like it just works. You have to have like much more extreme motion for that to take place. And a consequence of that speed of light being constant is that time can be dilated and distances or lengths can be contracted. And this leads to all kinds of things. You might, if you've read a bit, if you like reading about science literature, you might have read about the twin paradox, where, one twin stays on Earth and the other twin goes in a spaceship and travels very quick near the speed of light and comes back later. And the twin that's traveled like very quickly, comes back very young compared to their twin who has aged immensely during that time. And that's because if you travel very quickly, time goes at a slower rate for you. Well, for you, things still look normal, but compared to someone who's not moving, you would look like time is slower for you. So it's full of things like that. It's really interesting. And there's a book by I think it's no, that's on. There's a bunch of sort of popular science book about relativity that covers these sort of topics. If you're interested to read more. Anyway, so now moving on to the second theory that really made, and propelled Einstein to stardom, which is the general theory of relativity. And that one deals with gravity and also with accelerated bodies. So it basically deals with like all sort of conditions you could find yourself, if you were talking about motion of bodies and gravity, in space. So that's why that's the general theory. And in that theory, basically, talk about space-time. So, and that's the big, difference with anything that had been done before. Like to Newton and everyone before Einstein, you had space, which was, the three spatial dimensions, and you had time and space were different things. But what Einstein realized is that if you essentially multiply time by the speed of light, you basically get something that behaves like distances. And to all intents and purposes for calculations and like working out the theory, then time behaves exactly the same way as space behaves. So that's why you have something we call space-time. And the theory then deals with like explaining the motion and gravity of objects. But what's really interesting is that space-time is not just, space is not just something that's in 3D and just sort of flat, but space-time can be distorted. Space, the sort of X, Y dimension of space can be essentially bent, or the Y dimension, but it's difficult to picture it in 3 dimensions being bent, but it's easier to think of 2 dimensions being bent. And then time as well can be, distorted, which means that time does not flow at the same rate for everyone in the universe. And these are the mighty, I say mighty field equations, because that's the sort of E equals mc square, if you want, but of general relativity. And it looks like a sort of simple equation, maybe, I don't know, like I'm not going to start like, doing maths here, but you have like, a term on the left and it's equal to some term on the right. And then you have some constant, 8 pi, right, which is the constant pi, 3.14. You have g, which is the constant of gravity. And then you have the speed of light at the bottom to the 4th power. So you have like this sort of like equality, like E equals mc squared. except that in this particular case, you have like these little indices, and that's because this is what we call the tensor notation, and it basically describes what we call a matrix. And then these equations are in fact, well, this equation is in fact 16 equations. So you need basically 4 equations to describe each, of the 3 spatial dimensions plus the time dimension, if you want. But then there can be like connections between the spatial and the time dimensions. So then each space dimension can interact with another space dimension, and you need an equation to describe that. And they can also interact with time. So that means that you have 4 times 4, which is 16 combinations, basically. And this is what you need to be able to describe space-time and describe how matter and gravity behaves. So let me give you a bit of a sort of example of that. So imagine space-time, right, near the sun. Okay, so the sun is there somewhere. Now, we live in a 3-dimensional universe, but it's basically impossible for us to picture how space can be warped in a 3D space, because you need to kind of project these dimensions in an extra dimension to see how they could be bent without, but we cannot picture things in 4 dimensions. So the easiest way we can picture it is remove, say, the vertical dimension and just look at the world as if it was just on a sheet, right? Just sort of left and right and forward and backward. Now, because of the mass of the sun, it distorts space-time and it warps it into, making it like a bit of a bump. And that bump, because the star, because the sun is like a sphere, the bump looks like a perfect kind of like little valley, that's sort of like spherically symmetric. So it's just like a little hole, little dip. If the sun was bigger, and by bigger, I mean not in terms of volume or radius, but in terms of mass, then if the sun's mass was larger, the dip it would make in space-time would be deeper and would extend further. Okay, so mass is really what's the important quantity here in terms of distorting space-time. Now, what Einstein realized is that you can describe the effect of gravity on a moving body, or you can describe like the motion of bodies in space just by calculating the motion of that on that space-time sheet, by assuming that if there's no gravity and the sheet was flat, the object, right, if you push it at a constant velocity and you don't accelerate it to change its direction, it would just go in a straight line, a bit like what Newton had said, that if you don't exert any acceleration or any force on a body, it will just keep going in a straight line, basically. So the motion of bodies in our universe are just straight lines. But the addition of Einstein is that, this universe is not just flat. There are, near objects that creates gravity. Space-time is curved. So therefore, a ray of light, which normally would travel in a perfect straight line, this ray of light, which normally would go in a straight line, well, in fact, will follow a bit like, if you have a marble, right, on a surface that is not flat, the marble will go and will curve. So the light ray will go and can be bent by gravity. So therefore, from our perspective, it looks as if light was coming from that place, but that's because it's been bent. And it doesn't apply only to light, but also it applies to objects. So if you have like a planet that goes in orbit around the sun, what truly happens is, because of that curvature, right? The curvature around the sun looks like a bowl shape. And what the Earth is doing is a bit like, the cyclists, that is in that sort of like in that velodrome or something where the borders are bent and they just kind of like keep going in a straight line, following the line, but they just go around in a circle. So orbits are nothing else than motion in a straight line, but on a curved surface. And basically they follow that curve that is closed. And so they go around and around and around. Now, if you have an object that has more velocity or comes from far away or something, then it might come, follows the curve, and then whoop, gets swings around and goes somewhere else. And that would be the orbit of a comet, for instance, that comes from far away in the solar system, comes near the sun, and then swings around and again goes far and might just never come back. So that's the law of motion according to Einstein, in this upgraded version of gravity. So lots of very strange things going on. The other consequence is that gravity and acceleration are basically the same thing according to Einstein. And in principle, if you don't know that there's gravity somewhere, you could just think you're accelerating. And the best example of that is the example of the city astronaut in a space capsule that's got no window. So imagine you go in a space rocket, and then you're launched, and then you're in space, and the rocket is accelerating. You go towards Mars or something, and it's accelerating. Well, when you're in a bus or in a car or plane or whatever, and you're accelerating, you feel like you're pushed back right towards the seat. And in some fairgrounds and stuff, they have like this sort of like UFO game or attraction thing, right, where they spin it so quickly that you're actually stuck to the wall, and then they lower the floor and you kind of like just float there, right? So you could imagine that, if it was spinning fast enough, you could probably actually not just go like this on the wall, but you could probably like tilt yourself and have your foot planted, right, and be completely parallel to the ground. And so that's because of acceleration. In this case, it's the rotation, right? So the centrifugal acceleration, as we call, from the rotation of a body. But it works the same way if you're accelerating in a straight line. So the direction opposite, right, feels like that sort of like force that pushes you back. And the idea is that if you can accelerate fast enough, your feet will be glued down to the opposite direction, and you would feel just as if like there's gravity. And that's why people like fighter jet pilots, right, or Formula One drivers, they talk about G forces, right? So that which is the force compared to like the regular gravitational force that we feel on Earth. So when you hear, that, I don't know, Lewis Hamilton goes in a corner or something, and he experiences, 10 Gs, it means that like, it's as if he was like, forced like out or in his seat or whatever, like as if there was 10 times more gravity than on Earth. So if you can just get an acceleration in space or wherever else that is equivalent to 1 G, and it means you have to accelerate at 9.8 meters per second. So that's the acceleration you need to reach. If you go at that acceleration, you will feel just as if you were on Earth. So our city astronaut could be playing, bouncing a ball like basketball or something, and they would not notice that they're not on Earth. So you could have the same astronaut just right there on the ground in that same sort of box, and nothing would be different. So gravity and accelerations are, the same according to Einstein, except that in one case it's caused by the motion of a body, whereas in the other case it's caused by the mass of a body acting, on an object. All right, so hopefully, you can take like entire classes on relativity and such, at university. So there's a lot that we could cover, but I'll limit myself to that for tonight. But hopefully that gives you a bit of a flavor of what Einstein's theory of relativity is. So now let's see why we can use pulsars to test that theory. Why pulsars, and in particular, why binary pulsars? Well, the first thing is that pulsars are very stable clocks, right? So like I said earlier, they rotate and they produce this flash, and the rotation of pulsars is extremely stable. So on a short time scale of like a couple of years, they can fluctuate for a number of reasons. Like sometimes, the pulsation is not quite perfectly stable, or there might be, the pulsar and the Earth move around, and the sun, and we move around the galaxy, and there can be a cloud of matter passing in between that will change things a little bit. So there's a number of reasons why there might be small fluctuations. But over like sort of decade kind of timescales, like the rotation of pulsar is extremely stable because of they're such massive objects that are very dense. And so they're kind of like giant gyroscopes, right? So in space, right, or even in planes and whatnot, we can, or helicopter, we can determine the orientation of an object using gyroscopes, right? And a gyroscope is typically a sphere that spins very quickly. And if you move, but that sphere is free to, to rotate freely, then when you move, the object will keep rotating in the same direction. And if it's connected, then when you move, it will exert what we call a torque that would try to get it back, to its original pointing. So we can, that's sort of how, you can do inertial control and get your orientation, in spaceships and all kinds of things. So pulsars are basically giant gyroscopes that spin, and they have so much inertia that they slow down over time, but they do it very gradually. And it's very difficult, to stop them, basically. So the flash of light they produce is very stable. And that flash is basically like the tick-tock of a watch, right? So you can count time by counting the rotation, right? So on Earth, typically we define time as the, atomic time, right? Which is like the number of oscillation of cesium atoms. In the old days, we counted time as the ticks of a pendulum, basically in a clock. Then later on, we had mechanical devices or whatnot. But essentially, we're counting some kind of oscillations and define it as time. So pulsars, you can define time with them. The most accurately measured pulsar rotation is for this particular pulsar, and we can measure, and predict when the next rotation will be to a precision of about 10 or a few tens of nanosecond, in precision. So we know the rotation of the pulsar to so many decimal place. So the rotation of the pulsar is 4.57 blah millisecond, and the last digit is the uncertainty on that last number there. So it's basically 77, plus or minus 3 on that last number there. So it's insanely accurate. So much so that we're working on a pulsar timescale that will either help get better measurement of time, from atomic clocks by using pulsars to help, or will literally supersede atomic clocks, because they're more accurate. So that's something people work on. Then the other thing is that pulsars are extremely dense, and as such, they basically behave as if they were punctual object that had some amount of matter. So basically like textbook. And I'm saying that because, if you have a pulsar that orbits another object, and the other object is also, say, compact, then the orbit, is very easy to calculate using, Newton's or as we'll see, Einstein's equation. Whereas if you have two other objects that are not as compact, like say the Earth orbits around the moon, well, they orbit each other, and then we orbit around the sun. And okay, we can measure our orbit fairly well, but every day there are tides. So that's why there's this picture of the coast of a beach, is because there are tides, because the gravity of the moon and also the gravity of the sun actually deform, it changes the shape of Earth and makes it oblate, makes it elongated in the direction of the moon mostly. And so, and it creates tides. So the rock obviously is quite solid, so it doesn't get deformed, but the water on the surface of the Earth can actually be moved around, and that's what's creating the tides. And the thing is, when you have tides, right, you have like this big amount of like water that sloshes around and essentially creates friction on the ocean seabed. And so this kind of introduces like some sort of like jerking effect into the rotation of the Earth, which then also affects the orbit of the Earth. So things are quite a bit messy when you look in very details at the motion of the Earth, the moon, and the sun because of these tidal effects, for instance. But with pulsars, you don't need to worry about any of that because they're very compact, so there's no distortion. Now, if you put one of these superb clocks in a binary system, what happens is that the pulsar spin period will appear to change across the orbit. And that's due to a phenomenon we call the Doppler effect. Right? So just like a train that moves towards you or an emergency vehicle, right, that's got the sirens on, when it comes towards you, the sound it makes appears to be a higher pitch than if it was at rest, right? So you have like the train or Formula One or whatever comes towards you and it's like ee, and then when it goes away from you, then the frequency of the waves that you perceive is lower. So then it's like and goes on a lower tone. And so the way this apparent change in wavelength or frequency is what we call the Doppler effect. And a pulsar that orbits, around another object would have the same. So, that like sound of the pulsar we were listening to at the beginning, when the pulsar orbits, it would do like, instead of doing tick tock, tick tock, tick tock. Well, when it moves towards us, it would do tick tock, tick tock, tick tock. And eventually it would do tick tock, tick tock, tick tock, tick tock. Tick tock, tick tock, tick tock, tick tock. So you have like this change in the tick tock across the orbit. And it's a minuscule change, but because pulsars are such accurate clocks, we can actually measure it and we can track the orbital motion extremely well to basically accuracies of like millimeters for some of them. So, and that same Doppler effect, by the way, is the one that enables us to measure, the velocity of galaxies that led us to understand that the universe is expanding through that redshift. So, okay, so you can now imagine we can measure orbits really accurately for pulsars. The nice thing about pulsars is that they're also very massive, but they're also very compact, which means that then you can potentially find another object, say another pulsar or another neutron star or another small mass star, and you can make it orbit very close to the pulsar at very high speeds. And it's not something you would normally be able to do with the sun, for instance, because the sun, right, is fairly big. So you can only get another object, like a small, another small star. You could only get them as close as like touching each other. But the sun itself is what, 700,000 kilometers in size. So it's substantial size. But if you can shrink the sun to be 10 kilometers in size, and then you have another neutron star, which is also 10 kilometers, where you could imagine putting them at, only a few 100,000 kilometers from one another and orbit at very high speeds. And this is precisely what's happening in some of the pulsars that we observe. And when you do so, right, you're traveling at speeds that become quite high. And if you think back, at that example of the bow and arrow, right, from earlier, and then the fact that the speeds come, added fairly well with the, just the regular addition. But then when you had objects moving very quickly, right, closer to the speed of light, then things didn't add up, right? And then you need Einstein's theory to be able to add things properly. Well, it's just the same. So orbital motion of objects that is, that are going very fast will start behaving in strange ways that are not predicted by Newton's theory. So then you can start testing Einstein's theory, and you can try to see, if it works well or if you need something even better. So for the few coming slides, I'll be talking a lot about this double pulsar system. It's two pulsars orbiting one another. It's the only one out of the 3,000 pulsars we have observed so far where two pulsars orbit each other. There's about somewhere between a dozen and 20 pulsar where the other object is a pulsar, is a neutron star, but we don't see the other object flashing, right? It's not flashing as a pulsar. So you know that there's an object there because you can see, the pulsar is orbiting around something that you don't see, but the object is basically invisible. So one of the two spins very quickly, about 44 times per second, so 23 millisecond rotation, and the other one is slower, 2.8 second, and they orbit in 2.4 hours, for one full orbit. The distance between them is about the same as the Earth-Moon distance. Okay, so Earth around the Moon, right, takes about essentially 27 days or so for a full orbit. But here you take objects that are basically each 1.5 times the mass of the Sun. So the gravity is much larger. So despite, the same distance of the Earth-Moon system, because the masses are larger and gravity is larger, then it takes only 2.5 hours for a full orbit. So along the orbit, the pulsars move at speeds of about 0.1% of the speed of light or so. Is that correct? 300,000. Yeah, that's right. Yeah, about 300 kilometers per second. And so that's enough for us to, start talking about things behaving strangely. So one thing that happens, which Einstein actually realized, is you can explain why planets will drift over time in their orbit, what we call the Peyre-Astron precession of orbits. So it's something that was discovered by Le Verrier, which is a French mathematician, physicist, astronomer from the Victorian days. Le Verrier looked at the orbit of Mercury, which you see on the picture here. Mercury has been observed for, hundreds, forever, basically, by humans. And, starting with people like Tycho Brahe and Kepler, they made really accurate measurements of where Mercury is in the sky as a function of time. And people have measured Mercury's orbit, for hundreds of years. So using these data, what Le Verrier realized is that the motion of Mercury, which has an orbit which is a bit oval, right, an elliptical orbit, as we call, and here it's largely exaggerated. It's just so you can see it, because if you were to draw it to scale, Mercury's orbit more or less looks like a perfect circle, like to the eye, but it's actually a bit elongated. So if you look at Mercury's orbit, which is a bit elongated, what Le Verrier realized is that after each orbit, it actually drifts a little bit like that, a bit like a spirograph. And that precession, as we call, makes it drift and drift and drift, and eventually it comes back on its initial, after many, many orbits. And for Mercury, it's very tiny. So basically, over 100 years, it drifts by 43 arc of a second. So in other words, it drifts by about, there are 60 seconds in 1 degree and 60 seconds in 1 minute and 1 minute of arc in a degree. So 43 arc seconds is about 0.01 degree. Okay, so Le Verrier realized that the orbit of Mercury drifts by 0.01 degree per century. So it's really tiny, but accumulated over hundreds of years, it becomes apparent, and basically Mercury lags to where it should be in the sky by, a few, just a little bit. Now, no one could explain why that was, until Einstein. And Einstein, basically, because of that motion, right, in that bowl-shaped space-time, if you put an object and you make it orbit on an elliptical orbit, it will just naturally orbit in that ball, but it will drift over time. Now, that was really amazing, back, when Einstein published his theory, but we can do a lot better with pulsars. In that double pulsar system, it drifts by 17 degrees per year. So it's thousands of times larger in effect, than what we see in the solar system. So over 21 years, the pulsar around its other companion pulsar will drift, and do a full cycle. And so we, because it's so large, we can actually measure it, really easily. The other thing that Einstein predicted is that when two objects orbit each other, it comes a time where if they're not too far, the orbit actually drags space-time. So, space-time is not only, like curved, but when an object moves, space-time tries to move with it, but it's sort of like space-time is a bit like a bit viscous, a bit as if it was like honey or water, it's got some sort of friction. So if you move like a boat in the water, right, you produce waves. So the boat kind of like drags some of the water if you want, and it kind of like produces waves. So if you move a body in space-time, it will produce some kind of a wave. So essentially like that, that curvature of space-time has to follow the object. And that means like, there's kind of like a ripple that, carries that, that moves along. And so when two bodies orbit each other, you have like some rippling effect and these waves, they actually travel outward and they carry energy. And you might have heard about the fact that energy is something that is conserved, so you cannot create energy out of nowhere. So this means that if the ripples of the orbit is carrying energy away, it has to come from somewhere, and it comes from essentially the orbital energy of the system. So over time, two stars or two bodies that orbit each other will get closer and closer from one another. Now, for you to notice, you have to have big, massive objects that are close from one another, because if they're far, it's hardly noticeable. And this happens obviously with, the double pulsar system, or these pulsars that have a close companion. So in the mid 70s, two astronomers, Halls and Taylor, found a pulsar that's got a neutron star as a companion. It was the first time that they found like, a compact binary system with a pulsar. And a bit later, Taylor and another scientist realized that the orbit was shrinking. And that's what you see on this plot here. And they got the Nobel Prize in '93 for physics for that discovery, because this is the indirect evidence that gravitational waves are something real. So basically, if the orbit is constant, the two objects will come back, for a full orbit at, a set time, which is equal to the orbital period. If the orbit shrinks over time, then the object will come back a bit earlier, right, at the same point in the orbit each time. And so then if it keeps shrinking, it will come back earlier and come back earlier and come back earlier. So that will accumulate, right, and coming, in an earlier, point in the orbit when it comes back. And so that's what they basically measured. So if you look at the difference compared to like no change in the orbit, that would be like the line here would be no change, 0. And then what you observe is that basically the object comes back earlier and earlier. So in this chart here, it was made for the double pulsar, not the Halls-Taylor pulsar. So that chart basically showed that after, from 2004 or so when it was discovered to 2012, so something like, 8 or so year timescale, the orbit has shrunk so much so that the pulsar comes back at the same point in the orbit with a delay of about 4.5 seconds, over 8 years. Okay, so it seems very tiny, right? 4.5 seconds for for an orbit, that is, 2.4 hours, but we can measure, right? We can time these pulsars so well that it's measurable, and you can measure even like tinier changes than that. So, and the red line is what is the prediction from Einstein's theory. So basically, like the data, they overlap with Einstein's prediction completely, perfectly. So at this rate of the orbit shrinking, which is about 7 millimeters per day, right? So almost 1 centimeter. Right, imagine these two bodies at Earth-Moon system, which is about what Earth-Moon orbit is 1.2 light seconds or something like that. So I think about 400,000 kilometers, if I recall. So you shave about 1 centimeter every day from that orbit. And it means if you're patient enough, which means about 85 million years, then the two objects will actually collide. Like the orbit will have shrunk so much in 85 million years that the two pulsars will orbit and eventually touch. And then when they do so, they merge, and then they will turn into a black hole. But during the merger, some of the matter will probably be kind of like, expelled. And then it turns into a black hole, and the merger itself will shake up, space-time as well, and that produces a lot of gravitational waves. And these are what have been observed with telescopes such as LIGO a couple of years back when, we said the gravitational waves had been detected. And, that gave rise to another Nobel Prize, like 2017 Nobel Prize or something for physics, was for the observation of gravitational waves. And they were basically due to two black holes colliding, well, by now we also observe two neutron stars that collided. And when they do so, the ripple propagates in space. And basically we've been able to observe these ripples. Let me skip over that. That's a bit too technical for the good of the talk. But basically we can test Einstein's theory extremely well. So that was the second, like the one bullet point here. So we can test Einstein's theory to, well, basically the observed value that we can measure the theory compared to what is predicted by Einstein is basically, the ratio of them is about 0.9987 plus or minus 0.0050. And in fact, I should update that because there was a paper just last year that came out, which updated these, with new studies. And it's a factor of, I think it's a factor of 100 or maybe even more accurate. So basically Einstein's theory works completely flawlessly as far as we can measure it with pulsars. Now I just have one more, two more slides of something I want to show. Again, connected to the double pulsar. And it's the fact that, when they orbit these pulsars, they could orbit at any inclination compared to us observing them, right? I mean, there's nothing where, that should make the orbit one orientation or another, right? So the way we observe them is just luck. But luck is such that in this system, when they orbit each other, we see the system almost perfectly adjoined. Actually, we're only 0.5 degrees off from being completely perfectly adjoined. And because of this nearly perfect alignment, during the orbit, one of the two pulsars, when it passes in front of the other one, it screens the other pulsar that's behind. The screening is not caused by the hard surface of the neutron star, because the pulsar itself, like the neutron star, right, is only 10 kilometers in radius. So you will need the alignment to be completely perfect, more or less, for the physical body to screen the other one. But rather, what is hiding the pulsar behind is what we call the magnetosphere of the pulsar. So you can imagine a bit like around the Earth, because of the magnetic field of the Earth, we have this magnetic field, and then there's kind of like these belts that we call the Van Allen belts, right? And they contain plasma, they contain like particles that are trapped by the magnetic field of the Earth. But because pulsars have like such huge magnetic field, their surrounding is filled with particles, and it creates, some kind of like cloud, if you want, that surrounds the pulsar. And this is the cloud, that causes the eclipses. So when we look at the pulsar, how bright it is, as a function of time, we see that it dips and basically disappears or nearly disappears and then reappears. And this phenomenon lasts for about 30 seconds. So like I said, it's caused not by the star itself, but it's caused by the cloud that surrounds the pulsar. And what we discovered, and that's the work I've done, is that when we look at the same data, but instead of looking at about like 2 seconds per data point on this time series, when we look at data that is much more finely chopped off, and we look at how bright the pulsar is, we find that it is, it's a bit noisier because you split the data into smaller amount of data. But then you see that like there's like these sort of like, oscillations or like, sort of like periodic, like kind of modulation in the signal. So it disappears, but then it reappears and disappears and reappears and disappears. And so that's something one of my colleagues had found. And then what we realize is that basically the interval between them is exactly, the same. And it corresponds to the rotation of the cloud, which is synchronized with the rotation of the star itself. So basically this one, right, produces the light that we see here, but then the light becomes modulated by this cloud that's in the front. And so I've made another video. It's basically, I call it the donut model, that explains basically what's going on. So you have basically the cloud, and the cloud in that magnetic field, it has a shape that looks like a donut, okay, a torus. And the star itself, right, has a spin axis which is tilted compared to our sideline by something like 30 or so degrees. And then the star spins, and on the background, right, you have like the 2 orbits. So then the other star at the back is moving. And so we show with a little dot the motion of the star that's behind. And so if you look at how bright that star is compared to our sideline, it eventually will dip and fade away because the light crosses through the cloud that's contained within this donut shape. And so the object disappears, but then it always reappears initially twice per rotation because of the way that like this donut is toppling around. And eventually you get like to that part around here, which you see now, where now because of this weird rotation of off-axis donut, then it stays hidden for most of the rotation, but reappears just ever so slightly, and then eventually will reemerge, on the right-hand side. So that's the model we came up with to explain these eclipses. And you see in red are the real data, so they match like the model, like very, very well. And so what it enables us to do is working out the geometry of that pulsar that's at the front. Because if you were to change the tilt of the spin axis, or you were to align it with our sightline, or the other way around, you would imagine this would change how we would perceive, the pulsar that's behind, because it would get screened by the rotation, but because the geometry is different, then it would create like a different imprint. So we can measure the geometry of that spinning object very, very well. And what we realize is, by collecting data over a couple of years and modeling it very accurately, we realize, you can see here, you can see these pulsations through, and then eventually, like there's a gap, that appeared over time. And that's because the geometry is changing. And the way the geometry is changing is that the spin axis of that pulsar is not completely pointing in the same direction all the time, but it turns out it is precessing over time, a bit like a gyroscope, precesses like that. And this precessional motion is something that was basically measured, quantitatively for the first time using this system, and had been predicted by Einstein, but was not observed except, using experiments on Earth, but otherwise had never been observed. And the measurements we made basically agrees with the prediction of Einstein. So again, it's like one extra thing that we've been able to do using pulsars to test Einstein's theory. So I'll stop there, but basically the future is bright because we're working now on measuring changes in space-time due to gravitational waves, but using pulsars as essentially as like cosmic GPS that will able us to triangulate ourselves and hopefully detect gravitational waves, passing. So that's probably the next big thing in sort of relativity and pulsar gravity using gravity using pulsars. Thanks very much for your attention. I'm happy to take questions.
Thank you very much. Splendid talk. Guys, now we're going to have to work out how to do the questioning here. I don't think he's going to be able to hear where the other people are going to be able to hear unless we walk up to the front. Nick, do you have some recommendations? What did we do about questioning last time?
We were going to have a mobile phone on a long bit of call, but we haven't got that this time.
Okay, so Nick is talking. Can people who are online hear Nick talking?
Hello? Yeah, quite clearly.
Oh, okay. So we'll try this then. Okay, so guys, questions. Yes, Nick. Can you hear me is the question.
Yeah, can you hear me?
Yeah.
Rene, thank you very much. Very interesting talk. My question goes right back to the beginning of when you were talking about pulsars. And I think you may have answered it right in the last few slides, but I have a question about the cone angle of the lighthouse beam of radiation coming out of the pulsar. Is it possible to use that to characterize the pulsar in some way? And I think you started to answer that have answered it with what you were saying about eclipsing pulsars. Am I anywhere near right in that?
Yeah, so I mean, even an isolated pulsar, right? The pulsar itself is like an emission pulse that is quite unique, a bit like your fingerprint. And, there are people like some of my colleagues here in Manchester even who study these, specifically and try to like understand more about the objects and everything that goes on. In a way, the shape you see is sort of like representative of, our sight line. And maybe if I go to a slide I didn't really comment on very much, but you can imagine, that's the pulsar itself, right? And then what's in yellow would be sort of like that cone, right? If you were to project it in the skies, it sweeps, and then you kind of like take a still frame. And then like, if you look at the motion of our sight line compared to that cone, it's basically like a cut across. So what we see as the pulse, right, is basically the intensity along that cross, that crossing we make of the cone. And so then, looking at the pulse shapes enables us to try to understand a bit how that emission process takes place. So for a lot of them, you see only, this sort of like unique kind of like bell-shaped thing. So you can imagine the cone might just be like a bright sort of like fuzzy object that, fades away towards the edges. But then in some other cases, right, you see maybe two like these that are quite far apart, about half a rotation apart. So it might be tantalizing to think maybe that's both sides of the cones that you just happen to see. Some other cases, you see something like this. So that we believe is probably us cutting across a hollow cone where the rim of the cone is bright. And then it tends to be like, fainter inside. And then outside of it is like, there's nothing. So you kind of like get to this really bright thing, then it fades away, but, with a bit of a bridge, like some emission, and then goes back up again and then fades. And then you have like, the other ones like these, right, which are very messy, and then it's like a bit of a mess. But
the radiation at all, I mean, it's a spinning magnet, and it's not even spinning very fast. I mean, it's spinning a few times a second. It shouldn't be producing any radiation at all. Is the radiation caused by charged particles spiraling down the magnetic field? What is causing the radiation?
Yeah, the radiation, I mean, is quite something complex that is not fully understood, but the sort of the big picture of it is that because the magnet is so powerful, particles that are in the vicinity, they get attracted by the magnetic field, and then their motion follows the magnet, basically. So so then these particles, like near the poles, the particles will basically, they can basically move more or less only along the field, which is like sort of like away from the star or towards the star. And as they move, if they try to move sideways, they get repelled back, and then they will have like this sort of helicoidal motion. They will spiral, and it's something we see even around the Earth, right? With the plasma that's around the Earth, like, and that which causes the auroras. It's the same sort of like stuff. But what happens is when you have like these particles, like in these powerful magnets around pulsars, they spin so fast, right? They move so fast at near the speed of light, and when they do so, they produce light. They produce light through something that we call synchrotron radiation. So it's a physical process that happens if you accelerate the charge, and synchrotron radiation would typically produce radio light. So that's basically how more or less we think they shine, and why it's mostly along the poles. But there's a lot of details about where it's produced and over what range of heights, and then like how this if you inject a bunch of particles in a magnetic field like that, why it takes a specific geometry and not the other one, and blah blah blah. So all of that is not understood, and that's basically what people study by looking at the pulse shape. But something else you find is that if you were to observe the same pulsar, but you were to look at a different radio frequency, it would look different, the pulse. Usually it looks quite self-similar, but often, usually in most of them, what you see is that when you look at lower radio frequency, the pulse becomes broader. And again, the toy pictures, we believe this is because the medium is opaque to like radiation of a certain frequency, and only above a certain, that's what we call plasma frequency. So radiation can propagate through the plasma, but only above a certain frequency. So, and because the plasma is less dense and less magnetized at higher altitudes, then light can start escaping at a lower and lower frequency, but the cone of emission is broader. And that explains why the pulsars are wide, like the pulse is wider at lower frequencies. But again, there's so much we don't understand. But that plasma frequency, is the same effect. Why, if you're a radio AM, right, AM radio, the low frequency waves, they bounce back, on the ionosphere, so they don't propagate out because there's this layer of the Earth's atmosphere that's ionized, and it's opaque to very low frequency waves. So it's the same effect. So yeah, so anyway, that's the long answer, but yeah, there's a lot we can study by looking at
any more questions?
Yes, I have a question.
Yes.
How many of these binary pulsars have you observed and got results for? And also, how many other groups have been doing the same sort of thing, maybe with the same binary pulsars that you have? And are their results comparable?
So how many have we observed?
Yes.
So there are about 300 to 400 binary pulsars. Now, about I forgot the number, but something like 90% of them, the companion is a little white dwarf, and a lot of them. Well, I'm quite interested in them, and that would be another talk. But to study gravity. A lot of them are rather boring, if that makes sense. But the most interesting ones are among the sort of maybe 10 or so % of the pulsars left, which don't have a small object as a companion, but have a neutron star as a companion. And like I said earlier, I forgot the count, but I think it's 18, I believe, pulsar that have a neutron star as a companion. And these, the gravity is large, and these show like relativistic effects. And all of them can be used to test Einstein's theory. So they've all, and all of them are basically people gather data continuously, because the more data you get, the more precise those tests are. So they're really important laboratories, really, for gravitational physics. And all of them, all of them agree with Einstein's theory. So they're all in perfect agreement.
Precisely according to your graph.
So again?
Very precisely according to your graph.
Yeah. So the one we call the double pulsar that contains 2 pulsars, that one is the most, for a number of reasons, but it's one of the most compact orbits and the best and quite bright as well. So the measurements are good quality, and then the effects of relativity are quite large. So that one has the best measurements made, but the other ones are not used. It's not because you have one that works extremely well that the other ones are not important as well, because in some other systems, sometimes you can look at different effects, in different ways that you don't see in just one. And then also, if you want to fault Einstein, for instance, I mean, if it works in one system, okay, maybe you're just lucky for some reason, right? And then something that might manifest itself in a different context. So it's important to observe many of them.
Kabir, you have a question?
Yes, can you hear me?
Yes, you can.
Perfectly.
Very clearly.
Oh, that's good. I'm curious about one thing, is that you mentioned these very closely orbiting pulsars. And I'm just curious whether a pair of pulsars can get tidally locked. Obviously it doesn't, because otherwise we would see the spin to slow down. And why doesn't it get tidally locked?
Yeah, okay, that's a very good question. So maybe for everyone's sake, so tidally locked means a bit like the moon around the Earth, where because of the tides, because of the effect of gravity, the moon in the past was spinning much faster. I think as fast as maybe 9-hour rotation period or so, and was much closer, in fact, to where it is today. And because of the tides, it slows down the rotation of the Earth, but also it slowed down the rotation of the moon. And then the orbit, to conserve what we call angular momentum, the orbit of the moon has expanded. And now it made the moon rotation basically synchronize, right, with its orbit, so that it spins exactly at the same time around itself than around the Earth, which means it's on always the same side of the moon that's showed to the Earth. Now, in binary systems, like in general, if you have 2 like suns, let's say, and you put them at, I don't know, Sun-Jupiter distance from one another, eventually the rotation of the 2 stars will synchronize with the orbit as well, and they will show each other the same face. And that's something that happens, and it can happen fairly quickly depending on how far apart they are. Now, I now study another type of pulsar binary systems that we call spider binaries. And in these binaries, you have a pulsar and you have a low mass companion. And the low mass companion in these systems are not regular stars. They're more like brown dwarfs. So they're kind of like, super Jupiter type of objects, a fraction of the mass of the sun. And they orbit very close to the pulsar. Like we're talking about a few hours for the orbit. So the orbital separation is about the same as the solar radius, basically. And in these systems, we do see the companion star to be tidally locked. but the pulsar spins very fast still. And eventually the pulsar should slow down as well through tidal effects. But as I said earlier, pulsars are so dense and small that effects of tides are negligible basically on them. Because basically the effect of tides is basically dependent on the cube. You know, it's basically dependent on the volume of the object, if you want, like roughly speaking. So that's why, for instance, you know, a lake, you know, lakes don't have tides because lakes are, you know, have small volumes, and oceans have tides because, you know, they have like large volumes. So in theory, a lake does experience tides, but, you know, they would be microscopic and not measurable. So a pulsar does experience tidal effects, but they're so small because of the compactness that they're basically negligible. Now, however, if you pick two binary pulsars, right, and I said, you know, even the double pulsar eventually will merge, where as they get closer and closer from one another, then the tidal effects will become huge. And just before they touch, you know, they would start trying to circularize, and they will become very even elongated. But they will merge so quickly, right? When the orbit like starts shrinking, it will happen so quickly, basically, that the tidal circularization is difficult to achieve because it's on a slightly longer time scale. If I recall, I would need to double check the numbers, but yeah. So, but in principle, it does. But it's just the timescales are, you know, are not working out. And in a regular binary system kind of thing, even a double pulsar, they're too far apart for tides to act.
Rene, we're overrunning a bit. I would love to see if we can't do a couple more questions before we break off. Guys, are there any more questions from the floor here, from our junior section in this corner here? Any questions? No.
I was going to say the only question I have is more to do with the relativistic effects of double binary, and does, obviously with the two pulsars orbiting around each other produces gravitational waves, but does the spin of the pulsar, the speed of the spin, have an effect on the way the waves might be produced, and could that show itself as being somewhat chaotic in terms of the wave production?
Did you hear that question?
Yeah, I did. Well, so in theory, the spin does have an effect, but very, very small. So it's not, you know, for most of the gravitational waves that are produced, it doesn't really, again, it is so much smaller than it doesn't have any considerable effect. The only time when it would become relevant is near the time of the merger, because then the two stars, like we just discussed, you know, they become tightly distorted and kind of like a bit oblate. So then they're non-spherical anymore. And then at that point, it will become more, you know, more impactful on the shape of the, you know, if you were to have like two perfect spheres and somehow, you know, have the gravitational waves produce and it increases and then they merge, and they were to remain perfect spheres and everything, and then just somehow like just magically merge, you would have some kind of gravitational wave pattern produced. But then when the stars spin, then this would actually change the wave pattern during the merger. And this is actually something that LIGO and other gravitational wave detectors can measure. Now, this is, now, I must say, I haven't followed every single LIGO paper lately, because there's been quite a few, but you know, the first couple of papers I had read, and they were not able to completely characterize the spin, because again, it is a sort of like, you know, smaller effect on top of the main thing. But in principle, you can measure the spin. And you can tell even if an object is like counter spinning, you know, prograde or retrograde compared to the orbit even. So in the future, you know, with the increased sensitivity in these gravitational wave detectors and such, you know, it's definitely something that would be a lot more measurable, and it's quite exciting, right? So for instance, for black holes, you know, there's a big question as to how fast black holes rotate, because they do rotate, like it's possible for a black hole to rotate. And, there's the natural rotation of the black hole when it forms, right? And when the star implodes, the core of the star implodes and turns into a black hole, it will spin faster and everything, but it's probably far from the maximum, because a black hole has a maximum rotation speed that's possible to achieve, and it's probably very far from it. But then black holes also, they can accrete matter from a companion star and things like that. So then they can spin faster, just like the neutron star. And knowing how far or how fast black holes spin, then can tell you a lot about, their history, from the past that you didn't see. And there's all kinds of things about binary systems and, evolution of stars. But also about relativity and gravity, because there are theories of gravity, not other theories than relativity, that will predict the pattern of gravitational waves due to the spin and everything to be different from what relativity might predict. But then again, we're not quite there yet, but instrumentations are continuously improving. So eventually, it's the type of things that people would be able to measure.
Thank you. And anyone, one last question? Anybody got a question? I have.
Can I ask a quick one?
Sorry, but I'm going to give, who called?
I said, yeah, Steve, sorry, if anyone else is asking, it's fine. I had a quick question.
Oh, I'm going to take it in that case, so I'm going to ask the opposite. I'm going to ask, are there any binary, since we've got these very precise clocks, are there any wide binary pulsars that allow us to test gravity in the weak limit?
Well, so with pulsars, we're kind of like always in the strong limit of gravity, and if that makes sense, because they're so massive. To study the weak limit of gravity, it's more like in the solar system experiments, things like with the Pioneer space probes and the Venus probes, we can measure effects of gravity, like the bending of light. When, for instance, you send space probes towards Jupiter, towards Mars or Jupiter, then at some point they pass behind the sun, and then when they emit light, it goes through the curvature of space-time. But the pulsars with the white dwarf companions, they're really interesting on their own as well, because the white dwarf companion, you can actually observe, usually with optical telescopes. And we have extremely accurate model for white dwarfs, for white dwarf spectra, which can tell you what the surface gravity of the white dwarf is. It can tell you what the mass radius relationship is. And then if you're lucky and you can get some further observational insights, you can actually basically measure directly what the mass of the white dwarf is. And in which case, then you can also measure the mass of the pulsar, which is really cool because, we don't necessarily know what their masses are. But then the other thing is, in these white dwarf pulsar system, then the white dwarfs in many cases, will be in a very, very circular orbit because the orbit has been tidally circularized. So the white dwarf itself might not be tidally locked, might still spin at whatever, rotations rate it wants. But the interaction of the tides has made the orbit, which was maybe a bit, eccentric, a bit elliptical initially, it makes it circularize. And even more so because before the white dwarf formed, it was a red giant, that presumably transferred mass to the pulsar. Yeah. So that effect of mass transfer has created a lot of tides in the system, and they have very circular orbits. And it's a topic on its own, trying to measure how circular the orbit is, right? You try to measure the orbit and you try to measure the eccentricity, and you put a limit on the eccentricity. And I mean, it's unbelievably round, the orbit. Yes. And then what it enables you to do is then start doing other tests of gravity. For instance, if you have a white dwarf, in a very circular orbit around a pulsar, but that white dwarf, right, is orbiting around the galaxy, which is, a very massive So you can think of it as like a sort of like little moon Earth system orbiting around the sun, but except that, in this case, you have like the galaxy that it orbits, and then you have like the little, almost like little planetary system. Well, so there are theories of gravity that predict that that orbits should be preferentially aligned with strong gravitational fields. So it's called like polarization of orbits.
You mean like in the plane of the galaxy?
Say again?
You mean like in the plane of the galaxy?
Yeah, so not necessarily in the plane, but more like, if the orbit, if there was like some extra theory of gravity that was had like this weird polarization effect, then you would imagine, then the orbit of white dwarfs would not be perfectly circular, and it would be a bit elongated, and the elongation would tend to point towards the center of the galaxy, basically. So you can then use like as many as these white dwarf pulsar binaries, and you can look at like the small eccentricity that their orbit might have and see where it points, or look at the lack of eccentricity. And basically with that, you can essentially put a limit on that like polarization effect that some alternative theories of gravity propose. And they're quite stringent limits, in fact. And like you might ask, well, why, if Einstein's theory worked well, why considering other theories? But we have to remember the more general context, which is that, for instance, the early universe went through this completely crazy phase where, there was an inflation part, in the history of our universe, where it grew at an exponential rate for like a tiny amount of time, but that made the size of the universe go from the size of a golf ball to being like, insanely huge in like no time. And that's been caused by like some weird effect of physics that's kind of connected to gravity, but which we don't understand. And also when you look at the microscopic world, right, gravity and quantum theory don't agree with each other, right? They kind of clash. And so people have kept trying to find, this quantum theory of gravity, where string theory, right, is one of them. So basically, in some of these theories, like there are predictions like that, where orbits should be preferentially aligned towards, like, say, the center of the galaxy and things like that. And then using like these very precise orbits from pulsar white dwarfs, you can actually, put really big limits on these theories.
Very, very interesting. Well, listen, thank you very much again.